coming. Today will be a little bit different and similar in many ways. We're going to look at Linux. Some of you actually took the undergrad class with me where they actually did lots of Linux kernel programming. Many of the concepts have been going back and forth between the two operating systems. So in some cases, we can look at a little bit of history. Okay. We look at a little bit of history of how Linux started versus Minix and so on. There are just very few practicalities that I thought I would point you to. The Robert Log book, it's actually a pretty cool book. It's a very nice book. It's on a very old kernel version, like extremely old. We're talking old. Still, most of the concepts there have not changed, or at least many of them. Linux has been becoming more and more stable over the years. So this is also available in hard copy at the UMass library. You can also get it from UMass library as a legitimate ebook. You can also look around and see where you can find it. It's all over the place. Okay, so it's a pretty old book in many ways. So this is part of the course. It's not like we're going from Linux to Linux, which basically that does not basically mean that is this part of the course, is this part of our midterm exam? Yes, it is. There is an assumption that you guys know Minix, so I'm not going to compare explicitly between Minix and Linux, except in very few places in the slides. I would expect that in some cases you would see, okay, this is very similar to Linux, to Minix, and in other cases you would be like, no, this is different from Minix. So a very short history. So this is Linux started as a project from someone who was gruntled, who was very angry with how he could get Minix because of all sorts of licensing issues. An undergrad in the University of Helsinki. Is that? Okay. And I'm just wondering if it's too small. Okay. It is not the first try to do that. So Minix had its own licensing issues. There was a parallel effort also that was called the GNU project, which was basically trying to mimic or to basically rebuild the entire Unix ecosystem that started at Bell Labs. And everybody was angry at Bell Labs because, we wouldn't have Linux and Minix if Bell Labs had just open sourced Unix. Okay? It started in the early 90s, but people really took notice of it in mid-90s, and people claim that the first adopters were basically NASA trying to reduce the cost of buying an operating system that was free, so let's just use it. It's also Unix compatible, has all the different things that you would want from an operating system, so why not just use it? Linus, who started writing that code, is actually like a gut figure in that community. There are lots of flame wars between him and different people. He also is a little bit, profane. So he has these like flame wars with different people. I think you already read the Tannenbaum Linus wars on the kernel wars basically. But he does that all the time. I used in my class, I used to actually show people basically like a table with all the profane words inside the Linux kernel. You can actually go into the GitHub and search for everything that you can think of. You're probably going to find it. Right? People basically saying, please do not change this beep parameter because we don't know how to change it. There are also sorts of these things. Okay? This is something that you have probably seen. That is basically the Linux system model is very different from the Minix system model. What you have, and it's very weird to walk between these two screens. What you have is that you have applications running on top. These applications can only contact the kernel via the system call interface. okay, which serves sort of as a programming interface to the users. And then the system call interface can talk to different parts of the kernel subsystem, okay? And the Linux kernel is a beast. It's not a small thing, and we will actually see how beastie it is, okay? Each processor, each computer processor, each CPU is doing one of three things. It's either running a user process, okay, or running a kernel space process that is basically on behalf of something that the user wants, like write to disk, for example, or running a pure kernel process, basically running something that only the kernel can touch and only the kernel can work with, okay? It is a beast of different nature. You have no access to common programming primitives that you have if you're a C programmer, and that makes it a little bit harder to actually program. It's implemented in GNU-C, and there's a difference between GNU-C and SQC. We don't need to get into that. Now, this is the kernel, so you no longer have anybody to tell you, oh, by the way, you're accessing memory locations that you cannot touch. You need to reconsider, right? I mean, there are no protections. If you're on the kernel, if you are a kernel process, you have full control over the entire memory, okay? So kernel protection is non-existing, and that's for, that has two sides of it. We'll actually cover memory management in Linux later. But one side of that is basically, if anybody gains root, basically becomes part of your kernel, if anybody puts some malicious code in your kernel, you're basically exposed, because they can read your entire kernel memory space. Now, the kernel cannot execute floating point operations. This is actually something that there was I think there was a question on the syscalls if we should assume basically only on the integers, or can we do floating point operation? No, you always do. The kernel should never do floating point operations. Almost never. Okay. And that's not just for Linux, that's for any kernel, by the way. So as a kernel programmer, you do not just go in and say, oh, I'm just going to do some weird multiplications in there. The kernel has a small pair process fixed size stack. So each process that runs, and we'll talk a little bit about the processes later, has its own stack, has its own part of in the memory that is required for that process. There are asynchronous interrupts, so basically when I type on my keyboard, I am actually having my kernel stop to basically process the I/O that I have just sent in, which means that since I can stop at any point in the entirety of any process running, means that there are all sorts of synchronization issues that one needs to take care of, and concurrency issues that need to be handled. You can actually very easily get a race condition in the kernel. And I suppose that everybody here knows what a race condition is. Okay? Portability is important. Now, Linux is a pretty nice project because, well, it's small, it's contained. The number of lines of code is not that large. It looks very clean. But you cannot really run Linux on any hardware that I give you. Actually, you'll find running Linux on Raspberry Pis, there are people who are trying to port it, but it's not as easy as running Linux. So Linux is almost if it's a processor, Linux can run on it. Portability is very important for the Linux people. And that actually made Linux the go-to choice for many, many, many use cases. For non-power users who actually just use Windows, they do not really have, you have a Windows machine that will have either an Intel or an AMD core, and that's it. There are no other variations. But for power users who actually have, they're going to run this on an embedded system in a car, or they're going to run this on somewhere else, then this is important for them, servers and so on. Linux is a beast. This is actually one of my favorite graphs on Earth. So this is the number of lines of code in Linux as time progresses. And basically, many of the design decisions that were made in Linux in the early stages were basically saying that, we need to keep Linux small. But then all of a a sudden, like at 2.5 or 2.4 version, the lines of code just exploded. And now we are looking at 23 million, 25 million lines of code. I don't have track of the number. This is a few versions ago, and this is with the version numbers. Now, from a point of view of somebody who is doing systems programming, you have to understand that this is a huge issue. This is called code build, and one of the main issues with that is that as a programmer, maintaining 25 million lines of code, making sure that all dependencies are up to date, making sure that your code is secure, making sure that there are no bugs. This is the kernel. This is the thing that is actually going to talk and control your processor and stuff. Is a very hard task. I mean, there are different statistics on how many bugs does the most professional programmer introduce in each 10,000 lines of code. There are many statistics on that. There's an average number which I don't have it out of the top of my head. So now you have this 26 million lines of code that runs almost everything you can think of. It runs your servers in the cloud. It runs most of the database servers right now. It runs on many of the embedded devices. I mean, and so on. So how do you actually manage that? And there is a huge work now that's being done in developing the kernel.
Does that include driver code?
Yes.
So, if you want to support more hardware,
yes, but then this is why Linux can look much better. And Linux is in some way the most used operating system on Earth, but in other ways nobody really knows how Intel are using it. It's still something that never picked up. There is another kernel that Prashant has probably talked about, SEL4, SEL4, and this is a very interesting operating system because it's a formally verified operating system that actually runs as it does not run as a monolithic operating system. It's very similar to Linux. So people, especially in the defense industry and so on, they run SEL4. It's formally verified, so you know that the code runs. It's very small, so I mean the code base is very small, and then you can basically add only the drivers that you need, right? So there are all these sorts of issues. If you try to support everything, you end up with lots and lots of code, and this is why many people are actually trying to develop the kernel. That there are many things that are being done in that space. Again, floating point operations in the kernel are a very bad idea. Okay, floating point operations requires they take time. If you want actual real floating point operations, you're actually looking at precision. I mean, if you could just do like there are very simple multiplication and playing with the numbers that you do with integers that to basically make them floats and so on. But at the end of the day, this is not what floating point operations are. Floating point operations require precision. You don't do them in the kernel. You do them as user space. You want to keep them as user space for multiple reasons. Many of them architecturally based decisions. But again, it's something that you actually really need to take care of. I don't know how many of you will end up doing kernel programming, but it's something at least to keep in mind. Okay? Concurrency and synchronization. As I said, race conditions can happen and will happen in the kernel. Okay? So now how do you handle them? Now in your undergrad operating systems class, you have probably studied race conditions and different algorithms to actually detect them and so on. But as a general, and many of these are actually implemented in the kernel. But as a general concept, you need to always keep in mind when you're doing kernel programming. That's not just for Linux, but more so for Linux because everything is inside the kernel. Linux, I mean, if you're working at like the bottom layer, you need to take care of that also very much. Because if you're not working at the servers, even if you're working with the servers, you need to take care of race conditions, but you will not basically have, what we call the whoops, which is basically the kernel panicking. Okay? So Linux is a preemptive multitasking operating system. So you're running multiple things, which is similar to Linux. processes are scheduled and rescheduled based on some weird algorithm that the operating system implements. We'll talk about how Linux makes these scheduling decisions in a little while. But in general, I mean, you can't add your own scheduler, right? And the kernel must synchronize between these tasks. So you should make sure that, you know, if your task is waiting for I/O and it owns some parts of the memory, no other task is changing that part of the memory and these kinds of things. There is also the issue of interrupts, which is the same with Linux again. You have interrupts, and you have to basically make sure that the executing code, if interrupted, comes back to a state that is correct. Okay? And then basically, to do that, there are multiple techniques that are used in the kernel. We'll actually try to cover them in the course later. In some ways from the Linux source tree. However, you see that there are no servers. Everything is in the kernel. So you see that there's the drivers, there's firmware, there's the file system, the virtual file system interface. Now there is actually, some of these are quite interesting, like crypto, for example. Inside the Linux kernel, because you might want to do cryptographic operations in the kernel. Okay? So how do you do that? If I'm telling you that Linux has no access to libc or to any of the user-level libraries that you can use for cryptographic operations, then you either have to implement AES by your hand, which is a really bad idea, or they just provide it to you. So Linux has this wide number of algorithms implemented in the crypto folder, where you can actually just, like, inside the kernel, you can do cryptographic operations. Okay? Similarly, they actually have multiple other things that look, at the first sight, they are just strange. Like, for example, you have the sound subsystem is now part of the kernel, right? I mean, it makes sense to keep it up there, but it's in the kernel. I think there's one which inside, I believe, include. You also have a wide range of implementations of different data structures that you study in your data structures course. Double linked list, red black trees, you name it. They just go and implement it and add it to the kernel. Okay? So I mean, even because they want their kernel programmers to just have access to all of these things, and they want to make sure that these things are performing the way that they should. So there are lots of these things implemented inside the kernel. So Linux process management. So you guys have looked at the process abstraction. I mean, this is not new info to you. That you have a thread or process that share a virtual memory. I mean, there are no real boundaries, it's just virtual. And each of them have their own virtual processor. So to any application that is running, you give it the feeling that you own that processor. There is nothing else that works except that, right? And the program itself is not a process. The process is basically the program. The process is the active program itself. So the code itself, the data, the open files, and so on. And in the Linux code base, all processes are tasks. Any process is actually a task. Okay? And Linux has this elegant, very large task structure, which basically describes every single thing about a task. Okay? It's 500 lines of code. It's a struct of 500 lines of code. Okay? And it's actually, each structure is connected via a doubly linked list to other task structures. So all structures have like a task tree, okay? Or a task array. For a single task, the task structure can be as large as 1.7 kilobytes for a single task. So this is basically, this is everything you can think of that would be related to a task in that task structure.
So is this
task list like the same thing as the process table in Linux, or is that like what the same idea is, that it holds all these tasks are basically processes?
Yes.
Is process still in Linux, but it's a separate concept?
So,
So
the last part
you have a task, right?
Yes.
And you said that in Linux all processes are tasks.
Yes.
Is that basically just them giving them a different name, or is it that there's a different idea?
there are a couple of different ideas
Okay.
in there. So we'll actually cover some of them. So you have the task list, which is I believe that Linux does not have a task list, right? Where you actually have this double linked list and you have everything connected to everything. Okay? And this allows the kernel to actually quickly go through all the tasks that the kernel has. There's even an iterator that you can use to just like go through all the tasks if you want to get tasks, task information. That programs like edgetop, for example, or top, if you have used these two, they would just like go and read for all the processes, or ps minus aux, and these procedures. They would just iterate over the entire task structure, the entire task list, which is a double linked list, and basically to get all the information needed. Okay, and you can use that for all sorts of like operations inside the kernel, and they are definitely used as part of the scheduling, as we will see. Okay, so this is the task list. It's a double linked list. That basically each task basically points to the next task, and you have a parent for each task, and that parent is either the process that spawned it, the process that started it, or the init process, which I think is called the zero process in Linux or something like that, like the first process that ever starts. There's like a parent process for all Linux tasks, right? Is it called the zero process or something? I mean, okay. So you have the Linux process tree, and all processes are descendants of the init process. The init process is basically kernel starts the init process. Anything that runs links says that starts after init says that this is my parent. Okay. And the init process has a PID of 1, process ID of 1, and the relationship between processes is stored in the process descriptor. So in each task struct, you have process descriptor that basically has a pointer to the parent's task struct. So you either point to your init process, or that points to whatever process that started you. So if you are, for example, doing multiprocessing on Linux, and basically you start different Python processes on Linux, right? So the first process that you start, like Python, whatever, parallelize.py, is going to be your parent for all the processes that come in after that, okay? And basically, having that allows you to basically know like who started what, and to build an entire tree of your entire system. For each process, as we said, there's a per-kernel stack. And the stack is basically where the process has all its data happening, stored, right? Because each process will be operating on data. So suppose that you're parallelizing a web server. You're basically going to run some code to handle some requests, right? So basically, you need some data for each of these processes, and that data will be stored in your task, in your per-process kernel stack. Okay? And this is the highest memory address, and this is the lowest memory address, and then you will have the thread, the structure, the task structure towards the bottom of this. Okay? So towards the bottom of the stack, you'll have all the information for your task. Okay? We'll talk about threading in a sec. So process creation, just like Linux, uses fork exec, right? So I mean, it's the same idea that you divide how to start a new process to two parts, you fork and then you exec. And then you have the copy on write and all the things that Linux comes with. Okay? So just a reminder, fork basically creates the new PID, the new child process as a copy of the current task, and differs only in the process ID, and then the parent ID for that process in the task struct is now set to the original process ID, the one that spawned the new process. And then there are a few other signals that differ, but they are very few signals. Otherwise, it's an exact same copy. And exec basically loads the new executable into the address space and begins executing it. So it actually runs the actual code that should be running. And then you have copy and write. I think you also covered that, where you have you delay any changes to the struct that you just copied to the data that you just copied until you basically, so you don't actually write the actual data until you actually have a reason to write it, right? Like the new child is trying to change something in the data. So let's talk about threading in Linux. This is from last week. This is Linux basically. We have multiple user threads, all of them go to the same kernel thread. Okay? There is a single one kernel thread in Linux. Okay? This is Linux, where each user thread has an equivalent parallel kernel thread. Okay? So if you have 10,000 threads running for different applications, you're going to have 10,000 kernel threads that map to these user threads. Okay? This is actually old Solaris. It basically had M-to-N mapping of threads. So you might have 100 user threads that map into 4 or 3 kernel threads. Okay? This was implemented in Solaris, but now it's actually implemented in Golang. This is how Golang threading works now. And this is just a side note. Golang decided to go to that model where they have actually their own threading library that actually works on the different threads or the different routines in Go as an M-to-N. So they actually map M-Go routines or subroutines to N user threads. And there's a reason for them to do that. It's basically because it decouples concurrency from parallelism. So basically, if you're building a web server and you want to be able to support 10,000 requests per second, and you want each request to have its own thread, okay, to basically answer that. The way that Linux would do it is that for each of these requests or for each of these users, you're going to have an exact kernel thread that actually in the kernel, which basically makes the kernel, complicates scheduling and does all sorts of weird things. Basically on how large you can support things, you need to change parameters and so on and so forth. If you're writing this in Golang, then what you're doing is that you create 10,000 user routines, and these map to a smaller number of user threads that map to exactly the same number of kernel threads, and then context switching is much faster.
You said that this is threading implemented in the kernel? It is, right?
Sorry?
Is threading implemented in the kernel?
Yes.
So how does Golang get over that? It's just a
It's just it doesn't just like they have their own. I'm not entirely sure how it is implemented, but my understanding is that they have something that's just like the JVM in some way, and they implement that in the JVM. And I don't know what is Go.
some sort of virtualization.
Yes. I don't know what is the Go terminology for that. And actually, it's something that people have implemented also in other languages, like Erlang, for example. Which is the first very highly parallel programming language. Back to Linux. The kernel has no real threads in the sense that threading is supported in the kernel, but there is no separate notion of threads except that they're just another process to Linux. Okay? And then you need to manage the processes that map to the user level threads. They come back to the kernel as kernel level processes or kernel level tasks. And you need to do this mapping by just using the process tree and basically who's parent to what and so on and so forth. So everything in the kernel is a process. Okay? The kernel has no special data structures or semantics for threads in that sense. So it does not try to, for example, say that, you know, from a scheduling point of view, that task had, that user process had 1,000 threads, and that user process had 1 thread. I should differentiate between that. No, it doesn't try to do that. So that's 1,000 separate kernel processes, and that's 1 kernel process. So there's a total of 1,001, and then it will go through all of them. And each thread will now necessarily have its own task struct, because, you know, it's now just like a user level process. And Windows, Solaris, and many other operating systems have actually explicit support in the kernel for threading. So that's the difference. That's a huge difference between the two, or the operating systems in general. Okay. The only thing that you need to make sure of is that threads, they share process resources in many ways. So I mean, it's a way to basically make some shared data between different processes. At least this is what Linux views things. And threads are created using the clone syscall. Okay. And the clone basically has multiple flags. Did you cover clone by any chance? Okay, so what clone does is that, I mean, name says it all, it clones the parent. And then you have a huge number of parameters that you can pass to clone that actually controls how threading will actually occur. Okay? So basically you have, for example, do you clone files? Are the parent and the thread in the same threading group? Okay, so maybe the parent will just start the threads and doesn't need to be in the same threading group. Children will be together in the same threading group. Then there's like child set ID, create ID, and lots of other things that you can control how your thread is created, but by just passing these parameters. Okay. Now there is a very long debate on what to use. So you have now fork, bfork, clone, and there are a bunch of others that you can actually see in like the system calls library. And which one to use is a huge debate. Which one is better implemented and so on. So now we're talking about user level threads. Okay. Now we shift to kernel level threads, which are kernel level processes basically, and these are threads that the kernel stores for doing kernel stuff. Okay. There is no corresponding user level thread, so that means that you're basically only working inside the kernel. The user outside cannot control these threads, cannot kill it, cannot do anything to it. Okay. Although they are kernel level threads, they are schedulable and preemptible. Okay? So you can schedule them, you can preempt them. You can actually see the kernel level threads by just running ps -ef on your Linux machine. Okay? This should show you basically what threads are for the user and which threads are for the kernel. We'll cover a little bit more on this in different parts of the Linux lectures. We'll probably have 3 or 4 of them. And our aim is very high. We aim to finish the book in these 3 or 4 lectures. And that's basically because you guys have covered a lot in Linux, and many of the concepts are the same. So basically the idea is to give you like a huge dump on what is the difference between these two. So process and thread termination. Process destruction is self-induced. So there are 2 ways to kill a process. Okay, there's the normal way where the process basically finishes and thus dies. Okay, and then there's the sick term, basically sending signals to that process to kill it. Okay, if you're talking about like the normal path, the normal path is that you have the process itself quitting because it is done with whatever it was doing. And this occurs when the process calls the exit system call. It's basically a way for the kernel to know that, okay, this process is now finishing. And basically, once you have that system call, the process does not just disappear. This is not like no process. There is a process for the process to disappear. Okay? So first, this happens when it's explicitly ready to terminate. So it's literally the last line in your compiled code or something. Implicitly on return from the main subroutine of any program. So you have return, because basically that's the last thing that you need to return first and kill the process next. You do not kill the process and then try to return because, well, if you have killed the process, well, how do you return? Okay. So in reality, if you're calling a function or a method or something in your programming language, what you're doing when you type return is that you return and then you kill the process. Okay? It cannot be the other way around. It can be basically induced by the kernel using the sig term or some signal or some exception that happens. So if you basically, if a user level process tries to access, for example, protected memory areas, then in that case the kernel will kill it right away. Okay. Bulk of the work is handled by the doExit method, and that's defined in that folder and in that file. You can easily find them. And after the doExit completes, the process descriptor for the terminated process still exists. So, since a process is everywhere, I mean, you find it in your task structures, it might be a parent to another process, it might be a child to another process. I mean, that process cannot just disappear without cleaning all its traces. So, once a process calls doExit, it becomes a zombie process. Okay? And this enables the system to obtain all sorts of information that is needed before it actually kills the process, and thus do all the necessary cleanup for that process to actually terminate. Okay? We finished at 3:30, right? 3:40, okay. So, process and thread termination. So, first thing first, each process that has a parent, the parent is in charge of cleaning up their children, okay? As always. And the acts of cleaning up after a process and removing its process descriptor are separate. So I mean, the cleanup and then the removal of the process descriptor are two separate things. Parents, since the process has already returned, then the parent has already gotten a signal or gotten an upcall from the process that, oh, I'm done, I need to exit now. I'm a zombie now. Okay? So the parent has obtained information on its terminated child, or signified to the kernel that it does not care. So maybe the parent just started a bunch of processes that it does not care about them. There are actually cases when you programmatically do that. And then the child's task struct is deallocated, so you start by wiping the child's task struct. And then after that, you actually need to clean up after your process. So the parent basically starts cleaning up, okay, this was my child, I cleaned that up. Now there's a case when your parent dies, okay? And if your parent dies, you need to be a reparent. The kernel does that by actually either reparenting a process to some other process in its thread group, and that might be your grandparent, for example. So maybe the process started a process, and that started a process, and then the parent dies, so you give the orphan child to his grandparents. Very simple mechanism. Okay, maybe you are completely unlucky, and the grandparent dies. Now since you cannot basically have the process just like wandering around having no parents, we need discipline in the system. So what the kernel does is that it reparents the process to the init process. And that's what we call an orphan process. And if you have been working with Linux long enough, then you know what an orphan process is. You can have cases when you kill the Python code that just started 10,000 threads, and the threads still run. Okay? Although the parent is dead, the program is no longer there. You see it in your memory. You see it when you type htop or something. And then basically what has happened is that all your threads or all your sub-processes, because actually Python does not have, did not have explicit threading, so you actually created new processes. So all of these processes ended up elevating to the edit process, and they started becoming their own thing. They're living in their own world. Okay? So then you actually have to go and kill each of these orphans by hand if you actually meant to kill all these orphans. Okay? So, or I mean, restart your entire computer, and then you have killed like the forefather and no more ancestry. Process scheduling. Okay? Any questions?
In Linux, if your kernel process dies, is that it? And you just panic and it's over, or is there another process?
Depending on what kernel process it was.
Because there's no like recurring inside code.
No, no.
If there's something before that dies.
No. Yeah, if it's something, if you do something, so the kernel, if a kernel process dies, and that kernel process was important, one of two things will happen. Okay? You'll either have a non-functioning system, which basically, for example, so one favorite part is sometimes the process that dies is your sound card, right? It's not that important, but still, I mean, if you're watching a video, it's kind of important. Then you end up with basically no sound, right? You can explicitly start in some cases, but not for all processes. If your process has basically died because it did something stupid in the kernel stack, basically messing up the memory, then you end up with a whoops probably, and the whoops is basically kernel panicking, and you need to restart your machine or something. So it depends on what process it is. If your kernel level process is just like a mapping to a user level process, then yeah, it's not such an issue.
So by like part of the kernel dying, do we actually does that mean like there's like a thread, like a kernel thread like we talked about that's executing, let's say, sound card driver code, and then there's also one that's not doing something else, but that thread has died.
Yes.
Basically.
Yes. So that thread, which is a process in reality, has died, and you have lost all this data. And some of them, I mean, some of them become very. I mean, if you are doing syslink Linux administration, some of them when they die, they actually drive the creation. And some of them just die because you installed something that did something into that kernel process, and you don't understand why. Process states, we know them, hopefully. So you have any process is either running on a processor or waiting for a processor or zombie, basically terminating, right? I mean, these are pretty much what you have. So task running, task. So you have basically task waiting for something. You have task running, okay? Here, task ready, but not still running, so it's in the wrong queue to run next. And you have some things that are actually waiting for termination or something, okay? So multitasking, Linux basically interleaves all these processes together, right? And that's what Linux also does. I mean, most operating systems are thankfully multitasking, okay? On a multiprocessor machine, you want, if you have 10 cores, you want your 10 cores to be utilized, different parts running on different cores, right? Linux uses preemptive multitasking, very similar to Linux. Basically, you have some way to actually say that, oh, this process has already gotten its fair share of running, I need to preempt and run something else, okay? Now, this preemptible multitasking is actually as opposed to cooperative multitasking. Some people, at some point in time, thought that, it's so bad that we kill processes, we need to repair them and so on. Let's do cooperative multitasking. They also said that it's so bad that we preempt processes. So let's let the process play nice, and an application will just stop using the processor, the CPU, because it's nice. And there are two failed operating systems that were designed that way: Mac OS 9 and Windows 3.1. These are ancient, like really ancient. Especially Windows 9. 3.1 is like I don't even know, it's before Windows 95, so it's early 90s, maybe late 80s. So these systems, they were built with the assumption that applications will be nice to each other. Cooperative multitasking is a design decision that people make when they are designing operating systems, and thankfully nobody makes this decision anymore. Okay? And this is why I'm mentioning it. So the evolution of the Linux process scheduler. Before kernel version 2.4, it had a very dumb, very simple Linux scheduler that was not scalable. It had lots of issues. It worked. Okay. Now in version 2.5, they realized that now multiprocessing is a thing. We have multiple processors coming out. We no longer have a single core and a single chip. So we need to be able to support multiple processors at the same time. And since the first one did not scale, let's try to build a constant time scheduler that basically takes O of 1. Okay? And they built, and it worked, and it could scale to hundreds, of course. This had several shortcomings, and the main shortcoming was that for interactive applications, and interactive applications is basically almost everything we use as users. Okay? It sucked. What would happen is that you would press a key, okay? And there was a non-negligible probability that you will wait for some time to see the letter typing, which is not really fun. So for word processors, for web servers where you're waiting for request responses, for all these types of applications, which are interactive applications, you had actually pretty bad performance. And I mean, in version 2.6, they introduced multiple new schedulers. So they were like, okay, these two did not work, let's just introduce a number and see which one works. Okay? The one that is most notable is the rotating staircase deadline scheduler. I believe this is very similar to the Linux scheduler, right? Because the Linux uses a version of that, the staircase algorithm. You guys have covered the Linux scheduler already, right? So you know that you have like the multiple queues and you jump between queues and you do all these nice things, right? So they introduced that, and there they actually introduced the concept of fair scheduling, which was borrowed from queuing theory. And this was actually before many basically interchange between the two communities, where people would implement something and then something else would get implemented in Linux. The completely fair scheduler basically was developed, which is actually the current version that people use. I don't want to sneeze into the mic. That's hard. It was rolled out in October 2007, so it's fairly now stable. It has been there for almost 13 years. And this is the default scheduler today. There is a very nice explanation in this link. You can read it. I'm sorry I have not supplied the slides before the lecture. We promised that we'll do better the next time. So basically, what people think that processors are going to do is that they basically say that, have one CPU, one single task, it takes 100% of the CPU, have two tasks, takes 50% of the CPU, where each of them, where they run in parallel, right? This is what people think that the computer is doing. Everything is running in parallel, running my word processor with my YouTube, with whatever, and I get the same, it feels like everything is running in parallel, nothing is stopping, right? In reality, what's happening is that you run a single task, you run for 100% of CPU, you run two tasks, you run a single task for 100% of CPU, you run four tasks, again, one only for 100% of the CPU. And then you play with the quotas and the time slices and so on. So you know that there are IO1 versus CPU1 applications from your undergrad operating systems course and from this course. IO-bound applications are similar to, for example, word processor, like your word editor, okay, or your favorite programming editor. While other like CPU-bound applications, more like MATLAB, when you're running simulations and you just press run and then wait for 10 hours and then get something. Or your deep neural networks, because you need to talk about deep neural networks, where you basically wait for weeks and then get some result, right? Now, for MATLAB, when you're running a simulation, if that simulation ends 1 second early or 1 second late, you wouldn't feel the difference, right? I mean, it took 1 minute and 1 second or 59 seconds. What is the difference? I don't feel it, right? For interactive applications where you're actually pressing stuff and, I mean, if it's sluggish, if your editor is sluggish, you're unhappy. So basically, what most processors try to now do is to favor I/O-based applications, where your actually interactivity is much more important than CPU-bounded applications. Obviously, the world is not like that because your MATLAB editor can, your MATLAB is basically you write code and then it's an interactive application, but then when you press run, it's more CPU-bound application. And then you want your processor to be able to, out of the blue, detect what is running right now and what phase the program is in. Otherwise, I mean, you get very bad performance. There's the concept of priorities, which all of these operating systems actually inherited from Unix, where you basically say there are two kinds of priorities in Linux. One of them is nice values. If I'm nice -20, that means that I'm very bad to everybody else. If I'm nice 19, then I'm very good to everybody else. I'm very generous. I'm happy to basically be kicked out of the processor. Everybody should run, and I'm happy, right? There's also real-time prioritization in Linux that is used for the real-time scheduler that carries values from 0 to 99, where basically now here -20 is I have a very high priority, I'm a very important person, run me. 99, the real-time prioritization, is I have the highest priority. Okay, so they're opposite in some sense. There's time slices where basically you have a quota, a quantum for an application to run for a processor, for the processor to run certain application. And CFS basically has a nice way of calculating time slices, which is a combination of both the time the actual quota that you have and the niceness values. Now this is opposed to Minix, where you have the different queues, and moving between the queues meant you have higher priority or lower priority. The way that Minix does things at a very high level is that it assigns a share of the processor. And by share of the processor, we mean that there are two applications, each one of them should get 50% of the processor time. Okay? And then adjusts this share using the niceness values. So it uses the niceness values as an actual weight to how things are scheduled. Okay? So let's give an example. Consider a processor that is running your favorite word editor, OpenOffice, and your favorite encoder, video encoder, HVAC. HEVC is basically an encoder, which basically means that it takes a video and does all sorts of very heavy processing on it to actually get to do the encoding for the video. OpenOffice is OpenOffice, our favorite word editor. So the scheduler ideal scenario would be that have the word editor run really fast. HEVC, nobody really cares if you encode the video in an hour or 2 hours. I mean, well, people might care, but it's not like if we're talking about 10 hours or 11, people, I mean, lose the notion of time more. Okay? Is it 1 coffee or 10 coffees that I'm doing? So the idea that in an ideal world, what you will have is that you'll have the word editor get the highest priority, and thus the highest CPU time. Since this is an I/O bound application, that means that it will be blocking on I/O for so long, too many times. That means that I can basically start running the HEVC during that time and make sure that it runs. Okay? But whenever the word editor needs CPU, it gets it. So other operating systems, the way it does that is that it gives higher priority and higher time slices to interactive applications, which is Linux has this implemented somehow. Linux guarantees the text editor a certain proportion of the processor, 50%. You have 2 applications, so you get 50%, right? When the word editor blocks, it runs whatever else is running, and which is the video encoder. And when it's back, it basically says, I promised 50% and you've only run for 1%, then you have 49% of the processor to actually take. So that way, interactive application can run whenever they need, because they got promised a pretty large, basically, proportion of the processor. Now, before I get into that, I will also cover it later a little bit. Now, the problem is when you have a very large number of applications, right? Because now it's no longer 50%. So if you're running maybe 100, 1,000, 10,000 applications, 10,000 threads on your server, can I remind everybody of the electronic usage policy in the class? Okay. So basically, what if you have 10,000 applications, then you're going to have a very small share of your processor, which means that it might not be enough for you to run things. And Linux has a solution to that. Okay, we'll talk about it later. One thing to note again, which is a huge difference between Linux and other operating systems, is that the scheduler is modular. Now, in Linux used to implement that by basically saying, okay, put the scheduler, all schedulers should be user-level servers, right? Linux does not do that. What Linux does is that it actually has multiple schedulers running in the kernel, in parallel, and you can specify what scheduler runs which applications. You can actually do that with a simple command line on any Linux-based system. And this means, this is not, I mean, it's a concept in Linux. I'm aware of people who have actually developed multiple schedulers and run them on Linux. But Linux, this is used every day, right? You have 3 main, very, very popular schedulers in Linux. And these are the CFS, completely fair scheduler. You have the real-time scheduler, and you have the deadline scheduler. And in many cases, you run all 3 of them parallel, especially, I mean, people who do real-time systems, they actually do that all the time. Actually, the real-time scheduler came out with a project in Europe where they were actually doing that for high, for basically for real-time systems, which are like, they're like embedded systems and stuff, where you actually have different real-time constraints and things. Linux has a definition of scheduler classes. Each scheduler has a class, and each class has a priority. So if you're the real-time scheduler or the deadline scheduler, your priority is higher than CFS. Okay, and there's like you pick based on different things. And the base scheduler is defined in kernel /sched.c. Okay. When you run, you always start with CFS, unless you basically say that I'm going to use something else. Okay, so CFS scheduler is the base scheduler that I'm going to use. You can see the different available schedulers here, but you can also see them in this very nice, clean snapshot that they took, where you actually have different definitions for the different policies. Okay, there is actually an idle policy for the process when it's idle. And this is mostly done for energy and power efficiency reasons that you actually have an idle processor policy for running the scheduler. Sched norm is basically your scheduling using CFS, sched FIFO, sched round robin, sched deadline, there is sched real time, and so on. Each one of these, you basically look at the different schedulers, the different scheduler classes you have. You pick a scheduler based on its highest priority, and you basically look at what tasks have been assigned to that scheduler. This is in comparison to Linux, but this is a snapshot from last lecture where you actually had, the concept is that you can implement everything. It was like a revolutionary idea in Linux to move the scheduler into the user space. But it's not really a revolutionary idea because Linux has had that support forever. It's just much more complicated and much more dangerous to write a Linux scheduler. I mean, the amount of info that you need to understand is huge.
So, while Minix having these user space schedulers with the idea that theoretically you could just like write a new scheduler without having to recompile the kernel, while in Linux you can choose the scheduler, but obviously it has to be pre-built into the kernel.
Yes.
Right?
Yes, you need to rebuild the entire kernel. But yet again, if you're writing your own scheduler, I mean, you're going to write something like 20, 30,000 lines of code. Okay? I mean, at least you're going to write something in the thousands. Unless you copy all the scheduler, because there are all these functions that you can actually just copy from the other scheduler, but suppose that you're writing it from scratch, you have this brilliant idea. It becomes a pain when testing, but at the same time, you're already writing the scheduler. You're at that level, right? So not anyone is going to write a scheduler server in Linux. Also, as you rightly know, there is the concept of Linux kernel modules, where you can actually write scheduler as an LKM, and this is something that we'll try to cover. And LKMs is Linux answer to how do I write a scheduler that is modular. And the way is basically to attach code to the kernel as you wish. There are many reasons behind picking CFS. Okay, I just wanted to make sure that I'm recording this. There's the start interactive process. So one revolutionary idea in CFS is that if there's an interactive process that has already used all its quota, you can start it once it becomes live, once it's runnable. Although it has used all its quota, because you know what? You need to average things across time, so interactive processes will always run, will take precedence. There is also another reason, which is a hardware reason. If you're aiming for portability, you're not supporting a couple of architectures. And by not supporting a couple of architectures means that when you actually, time in the processor does not have a watch to look at the time, right? So the way it does that is basically looking at its clock frequencies, how many ticks have happened since whatever, and these are drastically different between different processors. Some of them are very slow, some of them are very large. So all processors, when they talk about okay, I'm doing a time slice, there are things that needs to be understood about the hardware, like the clocking frequency. Now you can obviously change these parameters as you basically change for portability reasons. So if you're doing that for a different processor, but yet an idea that I'm not looking at time slices in absolute time. Is that I'm going to divide it and basically not care, because otherwise I need to calculate the quota for each one of them. There are multiple other reasons, so we'll not go into them. Fairness is an important thing. Yet again, fairness comes at a cost if you have a very large number of processors. If you have a very large number of processes, then you end up with a very small quotas for each process, right? So although fairness is important, it comes at the cost that you might have to do a lot of context switching in the system. So if you have 100,000 processes running, you do not, just context switching will kill your computer. And context switching is basically when you move from one process to the other, you need to do things regarding the cache. Okay, so you need to basically flush your cache, you need to flush your registers, you need to jump from one process task structure to another, you need to do all sorts of these things that take time. Very small time, but not negligible once you have a very large number of processes. So instead of round robin, so the way that Linux does that is that it runs round robin, starting with the least run process first. So it keeps track of what each process has, how long each process has been running, and each process runs for a time slice that is proportional to how much of the kernel that it should, percentage of the kernel it should take, but also as a function of the niceness values. Then, if there are too many threads, CFS defines the floor time. So, and that's by default 1 millisecond. Okay, so any process cannot run for less than 1 millisecond. You can't change that; it's a configurable parameter, but there are very few reasons for people to change that if they don't know what they are doing. So the implementation of CFS, you have time accounting, you have process selection, you have scheduler entry point, and you have sleeping and waking up. These are the 4 parts that one can look at. The scheduler entity structure is basically a structure that defines everything about the scheduler. Each scheduler has an entity structure that basically says that, okay, this is for each task. I have a time for which, and I'm looking for that time. I have a virtual runtime. That's how long my process has been running, number of ticks. Okay? And I have basically, if there are groups, there are different things that basically, if there's a parent and so on, pointers to parents and so on. But the most important part is the vruntime. It's the virtual runtime. And the kernel basically, oh, it's here. No, it's not here. The kernel keeps track of the runtimes and runs the smallest runtime process. We're almost done. And it uses a red-black tree to manage the list of processes. Now, this is partially what I told you about in the early part of the lecture, where I said that they implement lots of data structures, including red-black trees. I'm not going into red-black trees. Scheduler entry point, the first, like, hello, this is the scheduler. It starts at scheduler, a function called scheduler, and it's defined in kernel /schedule C, and it finds the highest priority scheduler, okay, because we have different classes, and starts by running that and running the different tasks in that priority. There are a couple of optimizations in the kernel. One of them is that a task that is waiting for a processor that is waiting for I/O can be either a task interruptible or task uninterruptible. And uninterruptible is basically a task that is waiting for I/O, did not get its I/O, so it's going to wait until it gets its I/O, right? So no matter how many times the kernel tries to start that task, the task is just going to ignore. Okay, task interruptible is basically a task that is sleeping. It's sleeping, but it's willing to wake up. It has its data or something. Okay, and these are among the cool things in the Linux kernel. I think with that, I conclude exactly on time, surprisingly on time. So any questions?